Hi, it's Mr. Anderson, and in this video I'm going to talk about acids, bases, and pH. But what is pH? Well, we've got to start by talking about water. And so this is a water molecule. Remember, we're going to have hydrogen here, 2 hydrogen atoms, and then 1 oxygen atom. And so what is pH a measure of? Well, the P stands, we think, for the power of hydrogen. In other words, the amount of hydrogen. Let's kind of add a little bit of the equation of pH. And so some kids get scared by the equation. It's not that scary. So pH, or the power of hydrogen, is equal to the negative log of the hydrogen ion concentration. So it's the negative log of that. And so it's the negative log, think of this as 1 in 10 million. And so pH of 7 is neutral, but if we ever have a value greater than 7, it's going to be a base. And if it's ever lower than that, then it's going to be an acid. And so what does pH measure? It just measures the amount of hydrogen ions or hydronium ions. And bases and acids are going to have different amounts of that. We measure that using a pH scale. And so distilled water is going to have a pH of 7. If we have anything higher than that, that's going to be a base. Anything lower than that, that's going to be an acid. But when you're taking a test, it can be somewhat confusing. And so let's say we increase the amount of hydrogen ions in a solution, so we're going to have more of them. What's that going to do to the pH? It's actually going to lower it, and vice versa on bases. And so watch out for that when you're taking a test.
Thank you for joining me today. We're going to talk about medical acid-base disturbances in patients. And the purpose of this lecture is to make acid-base demystified to you. Let's get some definitions down, because sometimes these are confused. So there's two things that you'll see a lot of in acid-base, and that is people talking about an acidosis. So acidosis versus acidemia. What's the difference between acidosis and acidemia? In fact, what's the difference between an osis and an emia in terms of anything? Alkalosis, alkalemia. And the way I like to think about that is in terms of a seesaw. Okay? You can imagine this big dichotomy in acid-base. You've got pH of 7.40, which is kind of where you want to keep things, right in the middle. And that's a neutral pH, and you can go all the way up to 7.45 and all the way down to 7.35. And what happens is you get processes that occur in the body. So let's say you've got a metabolic acidosis here, and you've got another metabolic acidosis occurring here. But over here you've got a respiratory alkalosis or another metabolic alkalosis. These are processes that can occur, and they're all occurring at the same time. And depending on the balance of these, because some of these could be big, some of these can be small, that's when you get your emia. So an emia is a state of being. You have hyponatremia, hypokalemia. These are all situations that are occurring in the blood. So the key point here is that an emia is a state of being, and that's basically completely determined on what your pH is. If your pH is less than 7.35, then you're going to have an acidemia. If your pH is greater than 7.45, then you're going to have an alkalemia. Okay? So what is an osis? An osis is a process. It's something that's actually occurring. You can have many different processes occurring at the same time. So is it possible for you to have an acidosis but be alkalemic? Absolutely. You can have something down here which is trying to push your pH toward the acid side, but if you have something bigger up here that's pulling in the other direction and it's bigger, you'll still have a alkalemia because your pH is greater than 7.45, but you could have an acidosis. So I want to start off with a little bit of equations that'll tell us kind of the basics for where we want to go. So what is the pH? Well, pH, as some of you all know, is equal to the negative log of the concentration of protons. So that's important because as the number of protons in the body goes up, okay, the pH is going to go down. And so we know that a low pH means more acid. And then this in the body is sort of put together in kind of an equation where H or water plus carbon dioxide is equilibrated with carbonic acid, which is H2CO3, which equilibrates with a proton plus HCO3 minus. Okay, so why is this important? Well, because everything in the body sort of goes along with this equation. And I think the big key here is how the body deals with this player right here, protons. Okay, because protons is acid, as we just saw. So pH, as we said, is equal to 7.35 to 7.45. And that's the normal range. And what happens if things go out of this range? Well, the body doesn't work so well. Proteins start to denature, and that's why the body wants to keep things between that range. And we'll see how it does that. PCO2, okay, is equal to about 35 to 45. And you kind of remember that because there's similar numbers there. So we kind of like 7.40. PCO2, we kind of like 40. So 7.40 is kind of the normal, 40 is kind of in the middle. And finally, for the bicarb here, the range there is 22 to 26, with the normal being about 24. Okay, so that is the middle of the range. Now, a couple of definitional issues. Sometimes you'll see the bicarb also listed as CO2. Okay, you'll see that on what we call a Chem 7 or something like that, or like a little graphic here that kind of looks like this. You'll see it like that, where you'll have the sodium, and we'll talk about this. You'll have the sodium up here, the potassium here, the chloride, and they'll say CO2 down here. Okay, that CO2 in that Chem 7 is really the same as bicarbonate. Okay, it's not the same as the PCO2. That's different. PCO2 is the partial pressure carbon dioxide. Here, this is the total dissolved CO2 synonymous with bicarb. So if you see CO2, it's the same as HCO3 minus. Just be aware that those are the same numbers, but that's different than the PCO2, which has a normal of about 40. Okay. The other thing that you'll see is a blood gas. Sometimes you'll see an ABG, and the form for that is you'll have the pH listed first, then you'll have the PCO2 second, and the PO2 third, and then you'll finally have the bicarbonate last. So a normal would be, for instance, 7.40/40/90/24. That would be a normal blood gas.
In order for our bodies to function properly, the pH of our blood has to be within a fairly narrow range. Our pH, so the pH of blood, needs to be between 7.35 and 7.45. If the pH falls below 7.35, you're going to be diagnosed, and this line is there's kind of a gray area here, but this is what's defined by the medical community. If your pH falls below 7.35, you're actually diagnosed with acidosis. Your blood is becoming too acidic. You have too high of a hydrogen ion concentration in your blood, or a hydronium concentration in your blood. If the pH in your blood gets above 7.45, you're diagnosed with alkalosis. Alkalosis. Your blood is too alkaline. It's becoming too basic. The hydrogen ion concentration in your blood is getting too low. And so you might say, wow, this feels like a fairly narrow range. How does our body put up with acidic molecules entering our blood, or basic molecules entering our blood? How can it handle that without our pH while keeping our pH in this range right over here? And the answer lies in something that's also useful for the transportation of carbon dioxide in our blood. And this right over here, these equilibrium reactions, we see that carbon dioxide, when you put it in the blood, which is primarily water, so carbon dioxide in aqueous solution, it will react, and we have some enzymes that help this along, but it will react to form carbonic acid. So let me write this down. It will react to form carbonic acid, which is a weak acid. This is carbonic acid, and then that can dissociate to form bicarbonate. So let me write that over here, bicarbonate, and a hydrogen ion, or when we know that that would just attach to a water molecule and become a hydronium ion. In fact, in your blood, most of the carbon dioxide in your blood is actually in this form right over here. But the topic of this video is why this is also useful for maintaining our blood pH in this range. Because these equilibrium reactions between carbon dioxide, carbonic acid, and bicarbonate, this is a buffer system. This is a buffer system. And the word buffer in our everyday language, it refers to something that kind of smooths the impact of something, or it reduces the shock of something. And that's exactly what's happening here. Well, actually, let me put it this way. If you were to just dump hydrogen ions, and if you didn't have this buffer system, then your pH would decrease. Your pH would go down, and if you do it enough, your pH, you would end up with acidosis. But lucky for us, we have this buffer system. So as you add more hydrogen ions, they're just going to be sopped up by the bicarbonate. So this set of equilibrium reactions is going to move to the left. So you're not going to have as big effect on pH. And similarly, if you dumped some base, let's say you dumped some base in your blood right over here, well, instead of just making your pH go up and possibly give you alkalosis, well, now the base is going to sop up the hydrogen ions, and then typically that would just make your pH go up. But if you have these things going down, well, then you have fewer of these to react and have the equilibrium reaction go to the left, and so the reaction is going to move more and more to the right. And so this reaction, you're just going to have more carbon dioxide being converted to carbonic acid being converted to bicarbonate. This whole thing is going to move to the right, and so it's going to be able to some degree replace the lost hydrogen ions. So this right here is a buffer system. It helps dampen the impact as if you have more hydrogen ions enter the system, or as if you have something sopping up all of the hydrogen ions. And it's super important for us, well, just being able to live.